Hi everyone, I'm Christophe Bardoul, Sales Director of Axis.
Hello everyone, thank you for attending to this presentation. I am Eric Cariou, CEO and co-founder of the company. Axis is a French company located in Paris. Our product are designed and manufactured in France. We are specialized in wireless communication for the railway industry, but we also supply products for the industry. We are a partner of Schneider Electric company.
Next slide, please.
The demand on onboard connectivity is increasing constantly and is driven by the needs in real-time CCTV surveillance in coaches for passenger safety, passenger entertainment, and HD video streaming. Our mission is to provide a reliable 500 megabits per second high-speed train-to-ground communication solution at 350 kilometers per hour. Our train-to-ground solution consists in access points deployed along the track side.
Access point there.
And two clients mounted on board the train for redundancy purpose with the VRRP protocol. Each client gives 250 megabits per second. The two clients totalize 500 megabits per second.
Yes. So what is roaming? So you have a Wi-Fi client that is connected to a Wi-Fi access point. And when the client connects to another access point, we call this roaming. So it's actually for the client changing from one access point to another. And in the Wi-Fi standard, the roaming occurs upon the loss of the access point. So the client loses the connection with the access point, then will start scanning and looking for another access point. So this is not very efficient, because by the time you lose the connection, you scan, you find an access point eligible, you associate, and you start transferring data again, you lose packets. And it introduces as well latency. So it's not efficient at all, what is in the standard. So that's why all the manufacturers actually, they have their own roaming. And one of these method is the proactive roaming mono radio. That means the client doesn't wait for the loss of the AP or the access point to start scanning. So while it is transferring data, it stops to scan to look for another eligible access point, then transfer data again, and so on. And upon some criteria that are predefined, then the client will actually roam. It's better than the standard roaming, but still it's not optimized, because while the client is scanning, it does not transfer data. So it's not optimized as far as bandwidth is concerned. So that's why we looked a couple of years ago for a solution to optimize this roaming, and we developed what we call Connect Before Break technology, or CBB. So this is based, it requires two radios actually. So the principle is actually very easy to understand. So you have two radios, one is scanning while the other one is transferring data. So you don't lose any packets actually. There's no latency. So next slide I will explain. So while the first radio on the equipment is transferring data, the other one is scanning, looking for, it builds a list of eligible access points. And the best one of the list, then it will start the authentication with this access point, and will associate to the access point. While the second radio is doing that, the first radio is still exchanging data with no interruption. And once, again, based on some settings, some predefined criteria, the scanning radio that is will actually connect to an access point, and then we'll send an ARP request multicast actually to inform the network that now the packets needs to be sent to its MAC address, and then so you have what we call convergence of the network. So this is what is explained here. So you have two radios or clients, if you prefer. So the radio one is exchanging data, so data transfer, while the second one is actually scanning, building its list of eligible access points. It will then associate, so the second radio will then associate to the best eligible access point. Then the network will converge with the ARP, with the GARP ARP, with the GARP. And the radio number 2 that was will then start exchanging data with the access point, with the new access point, and the first radio will start scanning. So alternatively, the two radios, one is scanning, the other one is exchanging data, and so on. Next slide.
Our solution are intensively tested in our lab, obviously. We use a Candela traffic generator and programmable RF attenuators to simulate the train in motion. This is what you can observe on this diagram. Next slide, please. Once test lab are completed, we start the field testing. As renting a high-speed train is unfortunately not possible for us, we use a supercar driving on an airport runway. This is what you can see on the picture. We do tests with the Audi R8 V10, able to reach a speed of 330 kilometers, sorry, which is quite close to the TGV cruise speed.
Yeah, sometimes we have a good time in doing our job, especially when we test like this on the field. So here, the process, so how does it work? So this is to actually, this is a train with some imagination. To simplify, we represented only the client at the front of the train, but you were shown before that there's a client at the front and a client at the back of the train. And on this Wi-Fi client, this is a rail box, by the way. Rail box, actually, this is our the product that is designed to be on board the trains. We've sold, we have like 20,000 of them installed in trains and metros all over the world, by the way. So this rail box has two radios. So first radio number 1, in this example, so is sending data to the ground network, an OCC, an operating control center on the ground. So sending data and receiving data from the ground, while the second radio number 2, so is scanning. Next slide, please. So radio 2 scanning, again building its list of eligible access points, finding the best access point in this list, and starting to authenticate and then associate to this access point. Again, while the radio 2 is doing that, radio 1 is still exchanging data, no problem, no packet loss, nothing. And upon some triggers, the radio 2 will decide actually to converge the network, so to send his GARP on the network. And next slide. So the network will be, on the ground will be informed that he has to send his packets to the MAC address of radio 2. And at that time, radio 1 will actually stop exchanging data and will start scanning. Okay, so now radio 1 is scanning, radio 2 is exchanging data, and so on. This is how it works. Next. We have actually a lot of parameters to decide when, at what time you need to roam. And these parameters actually, we introduce new parameters sometimes when we discovered on the field that the needs actually, it's very complex actually. The most difficult part when you on a project is to be able to set those parameters to have the best bandwidth and an optimized connection.
It's because the behavior of RF is not predictable. And so we must do measurements in tunnels so to check it, and sometimes we have to make some change in the algorithm and add some parameters to correct it.
Yeah, it really depends on the environment actually. Tunnels, but also the orientation of the antennas, the gain of the antennas, and so on. So those parameters. So first, a list of basic parameters, roaming parameters, the list of channels to scan, of course, the time between two scans, the level of current AP above which no scanning is needed. Meaning that if the signal level is good, there's no need to scan actually. Also, there are some conditions to select the candidate access point. Minimum, so it's the minimum signal actually to consider an access point as a candidate. Boost, this is the signal improvement that you want to see to consider the access point as a candidate as well. You don't want to roam just to gain 1 dB. The boost would be basically around 5 dBs, I mean, or something like that. Conditions to leave current access point for the candidate access point. So there's a leave threshold as well. Next, please. Yeah. We have also some. There's also some advanced parameters. Stability parameters. Sometimes the signal is actually moving up and down, and some hysteresis. So you don't want to actually you want to avoid this hysteresis. So there's stability parameters. Also a threshold measurement tolerance. Candidate access point parameters. Maximum signal level to analyze or to consider an access point as a candidate. You would think, why a maximum? I mean, if the signal is high, there's no problem. No. If the signal is too high, you may have some problem in the receivers, the radio receivers. You can damage actually the radio receivers if the signal is too high. So that's why we have this parameter maximum. No return delay as well. You don't want to go back and forth from one access point to another. So this is also a parameter that is used. Conditions to leave the current access point for the candidate access point. So a minimum delay between two roamings, some signal thresholds as well. RSSI smoothing factor. Actually, there's you can give a weight on the beacon sent by the access point, and you do actually an average between the couple of beacons. This is actually this parameter to avoid to have some sudden change from one access point to another. You want to actually to have a signal that is smooth. I mean, that is not doing this back and forth like this with sudden changes. You can roam also on the number of lost beacons. Next. And this is what is actually shown here on this diagram. On the top, the no scan zone. Why? Just to understand this diagram. So this is the signal on the current on the pink. This is the signal with the current AP, called APA in this case, access point A. And the green one is the signal, level of signal with another access point that is named here access point B. So the current AP, the current access point A, when the signal is higher than the threshold here, you don't need to actually to scan. The signal is good, you don't need to scan. Then this is the time. You can start when you cross. Actually, you move like this. From the time moves like this, going on the right. Below a certain threshold, you can start scanning because the signal is not that good. Do you have some criteria? Actually, this is to say that as soon as you have a candidate AP access point that is eligible, you roam. This is we call this the need a roam. Okay. There's also a threshold. This one, the signal is not good at all. So even if you the signal is not good, you stay on the current access point because the candidate, the signal is not good as well. So, okay, next. So the performance achieved, that we achieved by the test and also that we achieved on the field, because CBB is used actually on some metros in Paris, for example, on some metro lines in Paris. So it's a 0.1% of packet lost. So at 350 kilometers per hour, so this is our test. This is not the metros, of course, because 350 kilometers, it's quite fast. And what is interesting is that this is not dependent on speed and not dependent as well on the throughput.
Okay, as you can observe, building a wireless cable between the trackside and the train in motion is not trivial. So this is the reason why we had to develop this algorithm, which is pretty complex and with a lot of parameters. But this is a recipe to have something working very fine. It is actually deployed in Doha for on the metro of in Qatar for the metro of Doha and the tramway of Lusail. In perspective of the football soccer next year. It is also deployed on the metro of Panama and finally on line 4 and 14 of the Grand Paris Metro with French RATP and Atos Nokia.
Well, thank you. Thank you very much for